Okay, in this video, we're going to be looking at another aspect of aquatic chemistry, specifically equivalence points. Okay, now, particularly simple relationships occur, as you know by now, when the activities of two species are equal. Take an example where you choose the pH to be 6.35 at standard room temperature of 25 degrees Celsius. You can basically rearrange the equation into this format, that is K1 is equals to the activity of hydrogen into the activity of bicarbonate HCO3 minus divided by the activity of carbonic acid H2CO3. And then you substitute that to obtain the ratio between the activity of bicarbonate divided by the ratio of the activity of carbonic acid is equals to K1 divided by the activity of hydrogen, because you bring the hydrogen down, okay? And that is equals to, because you're given a pH of 6.35, 6.35 divided by 10 to the power minus 6.35. Now we assume a known activity of all carbonate species in the solution. Remember, in some other videos I've said that you need to know the activity of all the species. You need to know all the species that exist in your chemical solution for you to be able to solve certain things. Well, there you go. Here we are. So in this case, we have activity of carbonic acid plus activity of bicarbonate plus activity of carbonate is equals to the total amount of carbon dioxide. In this case, it is going to be 10 to the power of minus 2. The activity of the carbonate ion will be very low at this pH. Okay, what is the pH? 6.35. Now, at that 6.35 or lower, you will not really have any carbonate ion. So if we ignore the presence of carbonate ion in this overall equation, then you have activity of carbonic acid plus activity of bicarbonate plus activity of carbonate is equals to the total amount of carbon dioxide, which is 10 to the power minus 2. Eventually, this thing, when ignoring the presence of carbonates, will reduce to the activity of carbonic acid plus activity of bicarbonate is more or less equals to 10 to the power of minus 2. Well, for all practical purposes, since you have ignored the presence of the carbonates, okay, this is more or less going to hold true. You can actually calculate it out and see that for yourself, that you will get a number which is very, very close to this. Therefore, if you go back then accordingly, the activity of bicarbonate divided by the activity of carbonic acid is equals to K1 over activity of hydrogen to give you 10 to the power minus 6 over 10 to the power minus 6. Okay, you know this from earlier slides. The activity of both species being equal, therefore this must solve to give you 5 times 10 to the power of minus 3. Okay, you can work this out. Now, once you have that information, you consider the point where hydrogen ion concentration, this guy, okay, equals the bicarbonate ion concentration, okay, which is this guy. Where is that point? That point is here. Okay, at this point, where the concentration of hydrogen is equal to the concentration of bicarbonate, okay, the concentration of the carbonate ion is extremely low. Why? The pH here is about 4.2. Okay, your carbonates more or less come into role or existence at around pH 7, 7 point something. So in this case, you can forget about carbonates. And there's exactly enough hydrogen ion to convert all bicarbonate to carbonic acid. It means that at this point, if I were to take the hydrogen, stick it in with the bicarbonate, I'm going to end up getting carbonic acid. Because the only difference between carbonic acid and bicarbonate is, you guessed it right, one extra hydrogen, which you have here. All right? So from the perspective of the proton balance, The bicarbonate ion concentration is equivalent to the same concentration of carbonic acid at this point. Okay? Remember that the total amount of carbon dioxide at this case is 10 to the power minus 2. You need to define the partial pressure of carbon dioxide, and at the same time, you have to be careful with the pressure and temperature conditions and pH conditions. All right, this is the point EP. And EP basically stands for equivalence point. And this equivalence point in particular is known as the carbon dioxide equivalence point. Okay. Now, in a similar way, the point where carbonic acid and carbonate ion concentrations are equal. So let's look for it. Carbonic acid is here, carbonate is there. So more or less we're talking about this particular point. Okay. This is known as the bicarbonate equivalent point. And where the bicarbonate and hydroxyl concentrations are equal, they are bicarbonate and hydroxyl. So we're talking about this point here. This is known as the carbonate equivalence point. Right, since we have about 3 equivalent points here tucked under our files, let's look further. The pH of these equivalent points depends, amongst other things, the amount of carbon dioxide concentration. So carbon dioxide concentration, partial pressure of carbon dioxide, everything is very important. You need to know all these things before you can talk any further about what the equivalence points are and how the ionic species are spread in the pH log A diagram. All right, this is a very important point. The exact concentrations of carbonate species, okay, in your reaction basically depends on the total carbonate concentration. Many times we overlook this point. So in a pure system where you have just carbonate and calcium carbonate equivalents, okay, that shouldn't be a problem to identify the species and the exact concentrations of each species. But the other condition is very exciting because it says that the concentration of other ions in solution, okay, is a major factor that helps us identify the concentration of carbonate species. So let's say if you have something else, magnesium, sodium, so on and so forth, then it's going to be very complicated to determine the exact concentrations of your carbonate species. It is not impossible, it's just going to make it a bit more difficult. So therefore, if you look at the figure that was given to you so many times, we have actually specified the conditions in which case the total carbon dioxide content is 10 to the power of minus 2. Okay? In other words, you need to know the partial pressure of carbon dioxide. And no other ions are being present. In other words, the system is reasonably pure. Now, nevertheless, the distribution is known to be quantitatively similar for other conditions. Now, you have to approach this very carefully because for every time you work with a solution and solution chemistry, you need to be able to identify all the species. And after that, you need to be able to identify the concentrations. Or if you're working in modern times, maybe you're looking at the activity itself. So once you have all this information in your hands, then basically you can start to model the type of species, the amount of species, and so on and so forth. But for all that, the antecedent conditions, in other words, the partial pressure of carbon dioxide, the purity of the system, and the pH range at which you're working, all these have to be specified very clearly right from the very beginning. Okay, now I hope you have enjoyed learning this aspect of aquatic chemistry as much as I've enjoyed teaching it to you. And look out for more videos on aquatic chemistry. Happy learning.